Our lesson today is going to focus on limiting reactants. So when we've thought of chemical reactants before, we probably never thought about how much of each reactant I need for this reaction to go forward and create my products, and how much product is going to, be created, and how is the reaction going to end. Well, at some point, one of our reactants or multiple of our reactants are going to be used up. Whichever reactant is used up first is called the limiting reactant. Whatever reactant isn't used up, whatever's left over after the reaction is completed, after that first reactant is completely used up, is referred to as the excess reactant. So I have an example here that may be more applicable than chemical reactions to our brains as we start to learn about limiting reactants, and that's making a s'more. So when we're making a s'more, we always take, 1 graham cracker, break it in 2, put in 1 marshmallow, and put in probably more chocolate than anything else, and we make 1 s'more. But at some point, we run out of one of those reactants. Usually the chocolate goes first because it's coming in a chocolate bar, so there's only, maybe a couple pieces available to put into our s'more. We're usually also eating that on the side as we're waiting for our marshmallow to cook up. And so we're always left over with maybe a couple marshmallows or usually a lot of graham crackers. And so our limiting reactant there isn't going to be our chocolate, because once we run out of chocolate, what good is a s'more? So we're done making them. Our reaction, our creation of s'mores is over. You can also think of this like when you buy a pack of hot dogs and hot dog buns. Well, there's 8 hot dogs in a pack, but only 6 buns in one of those packs as well. So you can only make 6 hot dogs with buns from that purchase. So your limiting reactant there, your limiting ingredient is going to be your hot dog buns. You're always going to have 2 extra hot dogs that go bunless when you're making that for dinner. So the same can be applied to a myriad of different, life examples. So the other one that I have here is a sandwich. Sandwich takes 2 slices of bread and 1 slice of cheese. And whenever we go through a thing of bread, a bag of bread, we always end up with bread left over, usually the end pieces, and then they end up in the back of our pantry, probably covered in mold in about a week and a half. That's because our cheese packets only come with maybe 12 pieces of cheese or 10 pieces of cheese. So we always use up the cheese first before we finish out the bread. It's never perfect. So we can no longer make sandwiches once we've used up one of our ingredients. In a previous lesson, we've talked about using eggs to create pancakes. Say we needed 3 eggs to make 24 pancakes for our friends, but I look in the fridge and I only have 2 eggs, meaning I can only make 16 pancakes, so I'm limited by one of my reactants. Okay? We can do the same type of comparison with chemical reactions. So I have the example here of H2 gas reacting with chlorine gas, creating HCl, hydrochloric acid. So here's our reaction for that. Now let's say we take 3 moles of hydrogen gas and react it with 2 moles of chlorine gas. We want to find out which one of those reactants is going to be used up first. And the way that we are going to do it is we are going to determine how much product we can make based off of the starting materials of that reaction. So based off of the 3 moles of hydrogen and the 2 moles of chlorine. So the approach that we're going to do is to compare the amount of product that would be expected from each reactant, and whichever one is less, whatever reactant is less, yields the lesser amount of the product, is then our limiting reactant, because our limiting reactant limits the amount of product we can make, so it's always going to be the lower amount of product that can be made. So what we're going to do is we're going to start with our 3 moles of H2, we're going to convert it to HCl, and then in a second conversion, we're going to take 2 moles of chlorine and convert those to moles of HCl. So that's what I have here at the top of our next slide. I took our starting moles of H2 and Cl2, and I've converted those to moles of HCl using our mole-to-mole ratios for our balanced reaction. So here's our mole-to-mole ratio of hydrogen gas and chlorine, and here's our mole-to-mole ratio of chlorine gas and HCl. So when we do this conversion, 3 moles of H2 gas produces 6 moles of hydrochloric acid, whereas 2 moles of chlorine gas produces 4 moles of hydrochloric acid, meaning the maximum amount of hydrochloric acid that we can make is going to be 4 moles of HCl. Just like our hot dog and our hot dog bun, I can only make 6 hot dogs with buns because I'm limited by the number of buns that I can make, or buns that I have. I can only make 6 of those, even though I have 8 hot dogs in a pack. So I can only make a maximum of 4 moles of hydrochloric acid, meaning chlorine is our limiting reactant. That was the reactant that got used up first and produced our lesser amount of product. So chlorine is our limiting reactant, and hydrogen gas is our excess reactant. Excess reactant in this case means that there's extra hydrogen floating around in our reaction vessel that's left unreacted. So there's extra hydrogen gas in there rather than hydrochloric acid. So if we know what's excess, what we have left over, well, we can then calculate exactly how much was left over, exactly how much hydrogen gas is left floating around in our reaction vessel. We can calculate that. So what we want to do in order to calculate that is we want to take our moles of our product, our limiting reactant product, which in this case would be 4 moles of HCl, and we want to convert that back to the amount of excess reactant to see exactly how much of that excess reactant we actually needed. So we're going to take our 2 moles of HCl and convert it back to moles of H2. So doing this out is 2.0 moles of hydrogen gas. So in order to create 4 moles of HCl, I had to use up 2 moles of hydrogen gas. I started the reaction with 3 moles of hydrogen gas, and I only used up 2 moles of hydrogen gas. I used up all of my chlorine gas, so 2 moles of hydrogen gas reacted with my 2 moles of chlorine gas, and we got out the 4 moles of hydrochloric acid. I can now determine, based off of the number of moles of hydrogen gas that were used up in that reaction, I can now determine how much hydrogen gas is left over. So I started with 3 moles of hydrogen gas. I used up 2 moles of hydrogen gas, meaning I have 1 mole of hydrogen gas left over. If we go back to our hot dog example, I used up all 6 buns, meaning I used up 6 of my 8 hot dogs. So I have 2 hot dogs left over. I have 2 excess hot dogs that went bunless and probably went in the trash. So the concept here is the same. I know how much I started with. I know how much I used up in that reaction based off of the limiting reactant, based how much of the lesser amount of product that was made. And I can calculate how much of my excess reactant is left over. So when we're doing these calculations, we want to make sure we start our calculation with the lesser amount of product that was formed, because that's as much product that we can form based off of this reaction. Because after 4 moles of hydrochloric acid is produced, I have no more chlorine left. There's no Cl left because that's my limiting reactant. So let's take that and let's try this problem on our own. So it's a very similar setup. How many moles of water could be made from 5 moles of H2 and 3 moles of O2? I give you the balanced reaction below, and what I want you to determine is what is the excess reactant and how much is left over. So very similar to our last problem. What we want to do is we want to take each reactant, so we want to go from reactant 1, convert it to the product. We want to then take reactant 2 in a separate conversion, convert that to our product. Okay, whichever one gives us the lesser is our limiting. Lesser is limiting. Whatever is not the limiting reactant is then our excess reactant. So we want to take our product, convert it back to our excess reactant, and then take what we started with, subtract off what we used, and that's going to be our leftover. So, pause the video, take a second, do these conversions, reactant 1 to product, reactant 2 to product, determine what's limiting, determine what's excess, then determine how much excess is left over. So our plan to solve this problem is to take each reactant, so we're given moles of each reactant, hydrogen gas and oxygen. We're given the moles of each of those reactants and we want to convert it to moles of water. So we're going to start with our 5.0 moles of H2. And using our mole to mole ratio, we know that for every 2 moles of H2 there's 2 moles of water. So 2 moles of H2 for 2 moles of water. H2 is on the bottom because we want to get rid of it. Water is on the top because that's what we want our answer to be in the units of. So this is 5 moles of water. So when I take 5 moles of hydrogen gas, I can produce 5 moles of water. If we look at oxygen, 3.0 moles of oxygen and convert that to water, we put our 1 mole of oxygen on the bottom, we want to get rid of it, 2 moles of water on top because that's what we want. That gives us 6 moles of water. So, because hydrogen produced the lesser amount of product, okay, this is going to be our limiting reactant. So H2 is limiting. That means oxygen is excess. So the maximum amount of water that I can create when I react 5 moles of hydrogen gas with 3 moles of oxygen gas is 5 moles of water. I'm going to have extra oxygen in my reaction vessel. There will be extra oxygen because that's my excess reactant, but all of my hydrogen will be used up. All 5 moles of that hydrogen were used up to create those 5 moles of water. But not all 3 moles of oxygen were used up to create those 5 moles of water. So I want to determine how much is left over. So we start with our 5 moles, our lesser amount of product, so our 5 moles of water, and we convert it back to our excess reactant because that's going to tell us how much we actually used of that excess reactant. So we have 2 moles of H2O and 1 mole of oxygen. This gives us 2.5 moles of oxygen. So I only needed to use 2.5 moles of oxygen in order to react it with the 5 moles of hydrogen to create the 5.0 moles of water. After water got to 5.0 moles, the reaction stopped because there was no more hydrogen left. There was, however, oxygen left over. So we started with 3 moles of oxygen. I used up 2.5 moles of oxygen in this reaction. That's what our previous answer told us. So I have 0.5 moles of oxygen left over. So our answer here would be B, which is what we have there. Now, limiting reactant and a lot of our reactions assume that we live in a perfect world and our reactions go to completion fully with no interference from outside factors. We don't spill something in the lab. We don't have a contamination in our reaction vessel. Things don't go wrong. That's a perfect world. We do not live in a perfect world. We live in an imperfect world where things will go wrong. So what our actual yield is going to be different than what we thought we could have gotten. So in our previous problems, we said we needed to use, 2.5 moles of oxygen, and it reacted exactly with that 5.0 moles of hydrogen, and I produced exactly 5.0 moles of water. But that's not always the case because there are outside factors that may affect that yield of final product. So this is where we start talking about reaction yields, how much we actually yield from our specific reactions and comparing it to how much we should have gotten, and why things changed, why did that number change, what happened in our chemical reaction to affect that number. So we have 3 terms to define in order to discuss reaction yield. The theoretical yield is the amount of product that forms when all of the limiting reactant reacts to form the desired product. Nothing goes wrong. That's our perfect world assumption. So when I have 5 moles of hydrogen gas, it creates exactly 5 moles of water out. That is our theoretical yield. The actual yield is the actual amount of that product that we obtained from the chemical reaction. Maybe I didn't get exactly 5.0 moles of water out from that reaction. Maybe I only got 4.7, or maybe I only got 4. Something happened along the way. My reaction vessel opened and I lost some of my product. Maybe if it was a liquid, it spilled. Okay? Things go wrong. So our actual yield is the actual amount that we got out from that chemical reaction. The percent yield is then the ratio of those two numbers and tells us the percentage of the actual yield compared to the theoretical yield. So we have a new equation down here. Percent yield is actual yield divided by theoretical yield. Part over whole multiplied by 100. How much did I actually get? How much was I supposed to get? Multiplied by 100 to give us a percentage. So when we look at these problems, here's an example here. We want to calculate what our theoretical yield is and compare it to our actual yield. So our first problem we have here is, upon reaction of 1.274 grams of copper 2 sulfate with excess zinc, so we already know what our excess reactant is, so we don't care about it. There's enough there to do the reaction. 0.392 grams of copper metal was obtained. What is the percent yield? So I reacted 1.274 grams of copper sulfate, and then I got out 0.392 grams of copper metal. So the 0.392 is my actual yield. Whatever the student or the chemist gets out from that reaction is the actual yield. What we can do is use this 1.274 grams of copper sulfate and convert that to moles of copper to see how much we should have gotten, so we can calculate the theoretical yield. In order to do that, we have to use a mole-to-mole ratio, and in order to use a mole-to-mole ratio, we need a balanced chemical reaction. Luckily for us, this is a 1-to-1 ratio, so we have copper 2 sulfate reacts with zinc solid, and it gives us zinc sulfate plus copper solid. So everything's in a 1-to-1 ratio. So we want to take our grams of copper sulfate, grams of copper sulfate. We want to convert that to moles of copper sulfate, which we know how to do using our molar mass. And once we have moles of copper sulfate, we want to convert it to moles of copper and then grams of copper, because we have grams of copper metal as our actual yield, so they have to be in the same unit. So our actual yield units and our theoretical yield units need to be the same. So we want to determine our theoretical yield now, so we start with our 1.274 grams of copper sulfate. We're going to divide by our molar mass, which is 159.61 grams for 1 mole of copper sulfate. So 4. Now that we have moles of copper sulfates, now that we're here, we can convert it to moles of copper in a 1-to-1 ratio, so that's 1 mole of copper sulfate for every 1 mole of copper solid. That cancels out our moles of copper sulfate. We're left with moles of copper. And now we just use our molar mass of copper from the periodic table, multiply 36.546 grams of copper for every 1 mole of copper. So let's do that out. 1.274 times the 63.546, divide that by 159.61, and we get out 0.50725 grams, which with sig figs is 0.507 grams. Oops. Sorry, 3 grams. Sorry, 4 sig figs coming from the 4 sig figs of copper sulfate. So that's our theoretical yield, is that 0.5073. So theoretically, if I started with 1.274 grams of copper sulfate, I should have produced 0.5073 grams of copper solid. But my actual yield tells me that I did not do that. I actually made less. So we can now find the percent yield. So percent yield is equal to the actual yield, which is that 3.392 grams, divided by the theoretical, which is what we calculated to be 0.5073 grams. We multiply it by 100 to make sure we're in a percentage, and we get out, let's see, 0.392 divided by 0.5073 multiplied by 100. We get 77.3%, with 3 sig figs now coming from our actual yield value. So we theoretically should have gotten out 0.5 grams. We only got out 0.4 grams. So our actual yield was less. So I only produced about 77.3% of what I was supposed to in this reaction. So our last problem is another percent yield problem. So take a second, pause the video, look at what this problem is asking you to do. We want to find the percent yield of this reaction. I give you the balanced reaction. So you first want to determine the theoretical yield for this reaction and then use that to calculate the percent yield of this reaction. Okay, so we're going to do a very similar setup to what we did in our previous problem. We are going to start with first we want to identify what is our what is our actual yield versus what we're going to start our problem with. So the reaction produced 12.5 grams. So because it produced 12.5 grams, that's our actual yield. And we started the reaction with 32.9 grams of calcium tetrachloride. So here's what we're starting with, and then here's what we're going to be comparing to. So we're going to start with our 32.9 grams of carbon tetrachloride, CCl4. We're going to convert that to moles because the only way to go between carbon tetrachloride and CF2Cl2 is to use a mole-to-mole ratio. So we have, let's see, 1 mole carbon tet to 153.82 grams. Let's see, I'm going to run out of room here. Let's see. Then, once we have carbon tetrachloride, we use our mole-to-mole ratio. 1 mole of carbon tetrachloride is to 1 mole of CF2Cl2. And then once we have moles of CF2Cl2, we can convert that to mass, which is 1 mole of CF2Cl2 is 220.91 grams. So we take 32.9, multiply that by 120.91, divide it by 153.82, and we get 25.9 grams of CF2Cl2 out. So that's my theoretical yield with sig figs. So to do percent yield, I take my actual, which we said was 12.5 grams. We divide it by our theoretical yield, which we calculated to be 25.9 grams, and we multiply it by 100%. So 12.5 divided by 25.9 multiplied by 100 gives us a percent yield of 48.3%.